Good morning. Today will be the beginning of the end. We are starting the last session of transport phenomena, which is mass transport. And to be honest, among 3 sessions, mass transport would be the most difficult, okay? Because it is a combination of everything, and it is a little bit sometimes confusing to understand. So we have to go slowly on this part, all right? If we recall, we start with momentum, and we said that any kind of transport which is related to the flux itself can be divided into 2 parts, molecular transport flux and convective transport flux. Okay? In order to explain that easily, we talk about that in terms of energy transport. Okay? Molecular transport flux is basically conduction in energy transport, and convective transport flux is basically the bulk flow of energy by means of the flow of the fluid. All right? If we consider the molecular transport part, that is driven by what we call driving force. For energy transport, the driving force is the difference in temperature. Okay? In conduction, in heat conduction, you need to have temperature difference. So we always say that temperature gradient or temperature difference is a driving force for energy transport. In the same manner, for momentum transport, the driving force for molecular momentum transport is a difference in velocity. In other words, velocity gradient causes the transfer of momentum from one spot to another. In mass transport, you can guess that it would be the same thing. We need some kind of driving force, some kind of difference to initiate the flux or initiate the transport of the mass. And the most familiar terms or form of the driving force for mass transport would be the difference in concentration. We have learned from high school that whenever we have high concentration of solute in one point comparing to the other point, there will be a diffusion of the solute from one point to another, right? So therefore, basically, the driving force for molecular transport is a difference in concentration. And you always realize that molecular transport of mass is basically called diffusion. Okay? Now, it is a little bit complicated because we have to talk about concentration first. In mass transport, when we talk about diffusion, that means we always have more than one species in the system. We cannot say diffusion of pure species because whenever we have pure species, everywhere the mass will be uniform, everywhere is the same species. So there'll be no diffusion, okay? There's no such thing as self-diffusion. Whenever we talk about diffusion, that means we always have more than one species in the system. So now we're moving on from pure species or pure component system to multi-component system, okay? So if I start with pure component, okay, let's say of species A. If I pick a variable, density, in this case, because the system is pure component of A, this density can be written as density of A, doesn't matter. This is for the system, and system contains only A. And we know that for the pure system, this is called density. Okay? And you might not realize, or you may, the unit, this is kilogram per cubic meter. This is obvious. But you have to realize now, when we are in math session, this kilogram is a kilogram of A. per cubic meter of the system. All right? Now, if I introduce another component, let's say if I introduce a system of binary component, A and B. Now the system is no longer pure component. If I still want to calculate rho, which is density, okay? Now that would be density of the solution. Now we have two components. If this one is liquid phase, one would be called solvent, the other one would be called solute. The whole system is called solution, okay? Which one is solvent, which one is solute? Conventionally, it depends on the amount. The species with lower amount is called solute. The species with higher amount is called solvent, okay? If we want to define this density, this rho, now it is density of the whole mixture. If you consider these two different systems, you should realize that this density of pure component is always constant, okay? Of course it's constant because you cannot, regardless of how many A we have, if you add more A in the pure component system, the density remains the same because you add the same thing to the system. When you add more A, more kilogram of A, the volume of system increases as well. So therefore, this ratio remains the same. But for binary components, if I have 50-50 between A and B initially, and I add more A, now density of the solution will change. So that means this density depends on amount of each species. In other words, this density of the solution depends on concentration. Okay? Mathematically, this density will still be mass over volume. But the mass here is supposed to be mass of A and B together. All right? So I can say that this density would be mass of A plus mass of B over the volume. And this volume would be volume of the solution or the volume of the whole system. So therefore, this sometimes is still called density, but just to be clear, this is solution density. Okay? Now if I split this into two terms, I will get mass of A divided by volume of the solution plus mass of B divided by the same volume of the whole solution. The first term is very similar to this part for pure component. So I would say this one is called rho A, and the second term is called rho B. The point is, now you have to understand that this rho A in the solution is not the same. It is different than this rho A. This rho A in pure component is characteristic properties of component A. It is always constant. But this rho A depends on how much A we have in the system. So this one is not density of pure species A anymore. This one is called mass concentration of A in the system. Okay? So this rho A now can vary. Same thing applies for rho B as well. So each one is called mass concentration. So therefore, this one can also be called total mass concentration of the solution. Okay? Now, if I take rho A divided by rho, that's basically equal to rho A divided by rho A plus rho B. According to that, total concentration is equal to summation of mass concentration of each species. All right? So if you split this, you can get total mass, this is rho A. So therefore, there will be mass of A per unit volume of the solution divided by mass of A per unit volume of the solution plus mass of B per volume. Okay? And all these volume cancel out. At the end, you get mass of A per total mass. This is what we call mass fraction, or omega A. All right? This is defined as mass fraction. So you can say that mass fraction is a mass concentration of the species of interest divided by total concentration of the whole solution. All right? So this is for binary components. If I add more components, I would change from binary to multi-component system. Let's say I have 3 components, A, B, and C. Everything would be the same. I just add part of the C components here. So therefore, the total mass concentration would always be summation of all components. In other words, for multi-component system, total concentration would equal to summation of the mass concentration for all species. And you have learned from very long time ago that summation of mass fraction would always be 1, right? And mass fraction of any species would be defined by mass concentration of that species divided by total concentration. That's the definition that you need to know. Now you have to realize I can use either mass concentration or mass fraction. Either of these variables represents how much or how concentrated my species of interest is in the system. If I have system with high mass fraction of A, still it implies that I have a lot of A in the system. In other words, concentration of A is high. So therefore, I can also use mass fraction or difference in mass fraction to represent my driving force. Okay? So this one is a little bit different than energy part or momentum part, because in energy, driving force is always temperature difference, just temperature. Even though you may represent temperature in different units, deltas in Celsius, in Fahrenheit, in Kelvin, but they are still temperature. But here, for mass, concentration can be represented in many ways. You may have mass concentration, you may have mass fraction. All of them are qualified to be the driving force. Okay? And we will learn later on, you may already guess, we also have molar concentration and mole fraction. So there are a lot of things that you have to think about. All right? So this is introduction for the driving force or for the concentration. Now, and we learned that whenever we have difference in concentration, we will get molecular transport of mass. And the setup would be very similar to what we did in momentum and in energy. So basically you have system of thickness y at t equal to 0. You start, let's say, let's say this one is a piece of solid silicon dioxide. The whole system looks like this. This highlight pieces is here, okay? So this is thickness y. This is silicon dioxide. Inside, if at time less than 0, before time less than 0, I consider this piece by itself. At time equal to 0, I put this piece on top of this system, and within this system, underneath here is gas. Let's say it is helium. Why helium? Because helium is so small. The atomic size of helium is very small. It has ability to somehow penetrate into the silica solid here to the other side. All right? So at time equal to 0, concentration of helium underneath here would jump from 0 to some certain value. So let's say that if this is concentration, at t equal to 0, concentration jumped here. Okay? And I do not want you to be confused. This concentration, the dot here, supposed to be concentration of helium in silica. Okay? It is not concentration in the vessel here. It is concentration that helium dissolve in solid. So this, if you calculate mass fraction of helium, I'm going to call this one omega A 0, and I will call my helium to be species A. I'm going to call silica to be species B. All right? So omega A 0, how much it would be depends on how easy helium can dissolve into silicon dioxide. Okay? In reality, this number is rather small. It's not so much of helium can dissolve into silicon dioxide, but it is not 0. Up here, if I have air continuously flow above this slab, so that means if helium can penetrate through the slab, it will be wiped out right away as soon as it reaches this point. So I can say that at this concentration, at this point, concentration of helium would be 0. Okay? So that is at time equal to 0. And you see that the concentration down here and up there are not the same. So therefore, we have differences in concentration. That would give you driving force for mass transport. So there will be mass transport or mass of A moving from down here up there. All right? So at steady state, the concentration here would be still omega A 0. Up there is omega A equal to 0. And you guess that it would give you linear concentration profile. So moving of helium down here continuously up there create the concentration gradient or this concentration profile at steady state. Just like what we did for Fourier law and Newton law. Okay? So if I set up or try to correlate mass flow rate of A, this is W, This is omega, a little bit different. If I call this direction to be y direction, as always, mass flow rate of A in y direction now depends on what? It depends on the difference of this concentration. If I'm using this mass fraction as a driving force, so it depends on omega A0 subtracted by omega A, which in this part, it is 0, right? We keep this one to be 0. It is inversely proportional to the size of the slab. If the size here is really large, the mass flow rate will be really small. So it is inversely proportional here if I can put the area of the slab down there. Okay? It is also inversely proportional to the thickness of the slab, y. So y would be down there. All right? Now, if you look at the unit, mass flow rate is supposed to have unit of kilogram of A per second. Area would have unit of meter square. So you have kilogram of A on one side of the equation. The other side, this is mass fraction. So the unit of mass fraction, even though you always said mass fraction has no unit, it has a unit. The unit of this mass fraction is kilogram of A per kilogram of the solution. Okay? In this example or in this setup, the whole system is called solution. It is solid solution. So mass fraction of A is kilogram of A per kilogram of everything. So per kilogram of the solution divided by y, which is distance in meter. Now you see that unit on the left and on the right are not consistent. In order to get kilogram of A, we got both of them already, but we need to get rid of this kilogram of the solution. So if I multiply by kilogram of the solution, okay, on this side I have meter square. This one I have only 1 meter. In order to make it stick, I'm going to divide this one by cubic meter. Okay, so this one kilogram per kilogram of the system per cubic meter, that is density. Now, if you change proportionality into equality, you need another constant. This constant is called DAB. If you balance the unit, you see that this DAB is supposed to have the unit of meter square per second. All right? You have second over here. Kilogram of A. Yeah. Now, if in the same manner as what we did earlier for Fourier law, we want to confine our system to be really, really small, the mass flow per unit area would become mass flux. And in this part, mass flux will be represented by letter J. This is mass flux of A in y direction, or JAY, equal to this ratio. When you narrow down the system to a very small part, the omega difference in omega divided by y turns to be differentiation of omega A with respect to y. Okay? Rho would be the same, DAB would be the same, and this d omega by dy is essentially slope of this line. and this line has negative slope. But on the left-hand side, the flux is going in y direction, in positive y. So in order to get the consistency of the sign, you put negative over here. Okay? So this is called Fick's law, or Fick's law of diffusion. Okay? And you see from this picture that helium moves from the bottom part to the top part without assistance of any flow. There is no flow within the slab of this solid. The molecules or atoms of helium moves by itself. So this is molecular transport. So Fick's law is used to represent molecular transport of molecules in the solution. Okay? So this is mass flux of A in y direction. Now, if you set up equation for x direction and for z direction, you get the same form of equation, and then you can combine x, y, and z component together. So the left-hand side becomes vector. This is vector JA, flux of A. On the right-hand side, that would be minus rho DAB. Remember, this rho is total concentration of the whole slab. Doesn't matter whether you are considering x, y, or z direction. This total concentration remains the same. Diffusivity will remain the same as well. For this differentiation part for x, y, z component, you end up with del omega A. Okay? So this is Fick's law in three-dimensional. Now you have to realize that there are two things about Fick's law. First of all, Fick's law is not theory. Okay? It was derived based on observation of the experiment. Of course, it is not empirical. It relies on some facts, yes, but it does not rely on theory. So this Fick's law is not theory. Secondly, it was obtained from the setup using binary system. In the experiment, we also consider binary system of helium in silica. So it was derived for binary system. So Fick's law is applicable only for binary system. Okay? So you have to also, I want to clear this part here. If this is the whole system, if I add another compound in here, let's say nitrogen, okay, or air, let's say 3 components in this vessel, do you think the system still remains the same? Do we still get the same equation? According to get this, do we have to have pure component of helium in this vessel? The answer is no. Why? Let us think about that. Okay? The point is, doesn't matter how many species we have, as long as only helium can dissolve into a piece of silica, then we still always have binary system. If you consider size of the molecules, nitrogen and oxygen is very big compared to helium. So only helium can penetrate itself in the piece of silica. These two gases cannot. So if we consider the piece of silica as our system, in this slab, we still only have 2 components. Okay? In the same manner as when we blow air up here, we have nitrogen, oxygen here. It does not go down into the piece of silica because atomic size is too large. So that's how we restrict the system to be binary. So as I said, Fick's law is applicable only for binary system, and you have to remember that. This is the biggest limitation of Fick's law. And as I said, Fick's law is not theory, okay? In mass, in momentum, we have Newton's law. In energy, we have Fourier law. Neither of them are theory. All of them were obtained based on experimental in the same manner as Fick's law. All right? So in momentum or in energy transport, we have not discussed theoretical movement in molecular transport at all. But in mass, we can. So if in general, I'm going to discuss theory, okay? In general, for the system containing A and B, let's look into atomic level. Let's say I have gas A mixed with gas B. Okay? In gaseous state, molecules or atoms can move around randomly with atomic velocity. Okay? Let's say A is a small molecule, a small gas, small molecular size. So therefore, the small one should move faster. Okay? In the common sense, small one should move faster. According to thermodynamics, moving faster means it has high kinetic energy. Okay? High kinetic energy in atomic level. So I have 3 atoms of A here. They might not have to move in the same direction. Let's say if you have a container containing A and B gas, and zoom inside, you see these atoms running around or flying around with different velocity. This A may go this way. All directions may not be the same because each atom moves randomly. And also you have to consider that this velocity of this atom and velocity of that atom may not be the same. They are not the same, okay? But in general, they are quite large. Now, let me change this B. This is atom of B, all right? If my atom of B, let's say B is bulky atom, it moves slowly, okay? Of course, these two velocities are not the same, but they are in the same region, same range. You can see obviously that B is moving at slower speed compared to A. If we look at A first, okay, I'm saying that I have 3 atoms of A moving with 3 different velocity. I can find average velocity of A. Basically, mathematically, if I can measure velocity of each atom directly, just measuring it up, add them up, divided by 3, or add the magnitude of each one divided by 3, then you get the average value. All right? Just to make it easier, if you take this vector and you expand them into z-axis, y-axis, right? This one, let's say this one is VA, the vector. I can expand them into VA in y direction, VA in z direction, and x direction respectively. Now, if we look at y component only, okay, just for simplicity, let me look at y component only. I can find average velocity of A in y direction. Basically, I expand to find VAY for all components of all species, all molecules, add them up, divided by 3. This would be VAY. I'm going to define this variable, VAY, to be average velocity of A in y direction. If I do the same thing for B, I just focus on B, expand the velocity into y direction, and calculate the average value. I will get average velocity of B in y direction. I'm calling this to be VBY. All right? Now, if I remove the labels of atoms, remove every label, and consider all 5 atoms together, disregard whether they are A or B, just consider atom. Now you can have 5 atoms moving around with different velocity. I can now find average velocity of all 5 atoms, and I'm going to call this one Vy. Okay? So Vy is average velocity of what? Of everything. So everything here is called mixture. So this is average velocity of the mixture in y direction. Okay? Now if I draw the diagram, I can see that VBY would be short. VAY, on average, A would move faster, so the vector would be longer. Okay? What about Vy, the average of all 5 atoms, disregarding whether they are A or B? It can never exceed velocity of A, because now we consider whatever we consider contains B as well. So the average velocity of all 5 atoms cannot exceed this VA, and it cannot be slower than VBY. It has to be in the middle. So VA or Vy here must stay in the middle. Does it have to be exactly the half of this? Do we have to add them up divided by 2? Is this Vy? Not necessary. It depends on what? First, it depends on the velocity of each species. Secondly, it depends on how much we have. If we have more A, just like in this picture, the average velocity of the mixture should lean toward velocity of A. If we have more A, it moves down here closer to VA. If I have more B, it would lean toward velocity of B, right? So it depends on how much, or it depends on concentration. So if we realize that it depends on concentration, now we can somehow propose the way to calculate Vy. Because of course we cannot directly measure velocity of each component, okay? We can say that the way we take average, this is the average velocity of the mixture of the whole system, can be depending on velocity of each component and how much it has in the system. In other words, it depends on concentration. How can we use concentration? Right now we learned about 2 things. First is mass concentration, rho A, or mass fraction, omega A. Okay? If I take mass fraction omega A and mass fraction omega B, of course these 2 numbers is a fraction, is less than 1. When you multiply by velocity and add them up, this velocity cannot exceed the VA, cannot be lower than VB. So this is how one way, and I'm going to emphasize this is one way, only one way, not the only way. It is just an option, okay? It's one way to calculate average velocity. So this is how we take the weight of each component using the mass fraction. So sometimes we call this one mass average velocity. All right? Now, this part sometimes will be really confusing. So I'm going to go slowly. Now, once we set up VAY, VY, all right? If I take VAY, which is average velocity of molecule A, subtracted by VY, which is average velocity of the mixture, what does it mean? If you go back to the picture of molecules, this picture, and imagine that I have 5 guys, okay? Let's say if you have seen the broadcasting of a marathon on TV, there's a group of people gathering at the beginning, at the start of the marathon. Let's say this is marathon, okay? It's an event. And in the event, there's 2 classes. Old guy and young guy. Let's say A here is young guy. B here is a senior citizen attending this marathon. Okay? Once it starts, everybody will start running in some certain direction. Of course, young guy, they are more fit. They can walk faster, and old guy will be left behind. Right? If you look from above, let's say that let's say this is a road. I have A, 3 of A, running. I have B running behind. All of them are moving in this direction. Okay? You imagine this one is, all of them are running. In order to keep track of this group, let's say I'm going to broadcast this event through the television. In order to make that, I have to put some kind of drone on top of this group, right? So this is my drone, okay? It's moving with camera. If I want to keep track of the whole group as a whole, I'm going to position my drone to be exactly at the middle part of this group. Of course, the group is moving to the right-hand side. My drone have to travel as well to keep track of the group, right? The speed of this drone is the speed of the whole group. So therefore, my drone is moving with average mixture velocity. Individually, blue guys or young guys is moving on average with VAY, their own velocity. The old guy is moving with VBY, their own velocity as well. Okay? As the time goes, you see that, of course, the whole group would move to the right-hand side. And there will be separation between groups. You may have old guy left behind, like so. The group would expand because this guy is lag behind, this one goes forward. My drone have to stay in the middle, okay, with Vy velocity. If I want to calculate or measure how fast this guy goes, comparing to the drone, if you look from the television, you see that this guy is moving ahead. This guy, on the other hand, seems like they're moving backward. Actually, they're not moving backward. They're moving to the right-hand side, but moving slower. But in relative with the respect to the drone, you see as if this one is moving behind or moving on backward. All right? So what we are observing from the drone is relative velocity. Okay? So if I'm focusing on the blue guy. From my drone, I will see that on average, the blue guy is moving ahead, moving forward. On average, the red guy is moving backward comparing to the drone. Now, this equation, VAY, which is blue guy, subtracted by VY, which is my drone, tells me how much the young guy moves faster than the drone. In other words, how much my young guy is moving faster than the average of the whole groups of the runner. All right? If you look at the unit, this is meter per second. If I multiply this by the number of species of interest, rho A. This rho A is kilogram of A per cubic meter. Just look at the unit. I will get kilogram of A per square meter per second. And it seems like flux. It's a flux of A per unit area per second. But is this really a flux? You have to realize this. Kilogram of A per cubic meter, if I draw a cube, and if this is y direction, okay? Kilogram of A per cubic meter means within this cube, how much A we have. Okay, just take A, measure its mass, and calculate it divided by the total volume. All right? If I multiply by velocity, this meter and one of these meter would cancel out. All right? This meter, if I highlight this one in red, is meter in y direction. All right? So this is length in y direction because this is Vy, velocity in y direction. This meter is the distance traveling in y direction per second. So this meter is meter in this direction. When you canceling this part to one of these meter in the cube, basically you're canceling this one out. All right? So this red line cancel this part, this dimension of the box, leaving only this area. So when you cancel this one up, you get meter square. Okay, you get 1 meter, another meter. 1 meter or one direction here is in x direction. The other one would be in z direction. So highlight with the blue ink over here. And you see that it is kilogram of A traveling in y direction per this unit area. And you see that the unit area highlighted in blue here is perpendicular to this y direction. So this is the flux. So basically, theoretically, this one is flux. It's flux of A in y direction. All right, so this is flux of A in y directions, and it is molecular transport because now we are considering each molecule moving on its own power. So it does not flow along with any fluid. It moves by its own power. So this is molecular transport flux. So in mass transport, we can represent molecular transport flux or diffusion flux in two ways. This one is the generic way. This is according to theory. Or you can use Fick's law that's restricted to binary system. Okay? Now, if I write the same thing for species B, VBY subtracted by VY, that will be velocity of species B with respect to average velocity multiplied by its concentration. That would give you JBY, flux of species B in y direction. Okay? If you add these two equations together, on the left-hand side, let me rearrange. I get JAY plus JBY equal to, combine these two terms together, I get rho A VAY plus rho B VBY, and then these two terms together, so I have minus over here, rho A VY plus rho B VY. Okay? For the first part, if I say that rho A is basically omega A times rho, remember from the very beginning of the class, mass concentration of any species can be equal to mole fraction kun total concentration. In other words, mole fraction is defined based on mass concentration per total concentration. This one is also omega B times rho. So I can take rho out. Inside I get omega A VAY plus omega B VBY. That's first term. For the second term, I have Vy here and Vy over there. I'm going to take it out. So I get rho A plus rho B times Vy. All right? This part, this is summation of mass concentration, that is total concentration, total mass concentration, rho. This part is according to what we defined earlier here, right? The average velocity can be calculated based on velocity of each species according to this exactly the same equation. So this is basically Vy. And you see that the first term and the second term are the same, so they are canceling each other. What does it mean? It means, of course, bluntly, I would say it means that the summation of the flux will be zero. But physically, these two are vectors. After adding become zero, it means that these two, not only they're equal in the magnitude, but the direction are opposite with respect to each other. Okay? So if we go back to this picture and take a look, VA subtracted by VY, basically you take this vector subtracted by this vector, so you have to inverse or reverse direction of this blue vector, and the net vector goes this way, right? So this is VAY subtracted by VY, which corresponds to direction of JAY. On the other hand, VBY subtracted by VY, you take this VBY and inverse or reverse this direction of the arrow, and you see that the result is going backward. This is VBY subtracted by VY, which corresponds to direction of JBY. And according to this picture, you see that flux of A is going in one way, while flux of B is going on the opposite way. That's why when they add together, they cancel out, become 0, and it is always 0. Okay? So you have to remember one thing, that summation of any flux would always be 0. Okay? This is the case for molecular transport. It is not restricted to binary system. This is applicable for any number of species in the system. All right? Now, a little bit before we moving on, this reverse direction of JBY is the same thing as when we observe this red guy moving backward from the drone. So that means the flux, the molecular flux itself, is described in relative to the whole population. Okay? So if you imagine that this direction represents movement of one species, this direction represents the movement of another species, both of them describing the movement with respect to the whole population. So molecular transport flux is not absolute value. It is the value regarding the number, but in terms of direction, it always be reported with respect to the whole population. Okay? Now, so even though I write this equation for y direction only, it is also applicable for x direction and z direction. So that means the total flux JA plus JB would be 0. Now, if I consider binary system only, then the Fick's law is applicable. So if I write down equation for JA using Fick's law, that would be minus rho DAB del omega A. For JB, that would be exactly the same, except that diffusivity, this is called diffusivity by the way, diffusivity would be diffusivity of B in A. What does it mean, A in B and B in A? This is diffusivity of A through the layer of B. So A is trying to squeeze itself through the crowd of B. This one would be the movement of B through the crowd of A. All right? Times del omega B. That's equal to 0. And now since we are in binary system, omega B, which is mass fraction of B, should equal to 1 minus omega A. Remember, summation of mass fraction is always 1. Okay? So if you take derivative, del is derivative. So you get derivative of 1 minus omega A should equal to minus del of omega A. Just like d of 1 minus omega A should equal to minus d omega A. So I'm going to plug this back here so you have del omega A on both terms. So if I take the common term out, I will get rho del omega A. Inside that will be DAB. Subtract. These negative signs come from here. Okay? And dBA. That's equal to 0. This side is not necessarily 0, so that means in order to make this equation 0 all the time, it means that this term must be 0. Being 0, it means DAB would equal to DBA. What does it mean, DAB equal to DBA? It means that the way A moves through a crowd of B would be the same as the way B would move through crowd of A. So imagine you go through bus terminal or subway and you have a lot of people going out from the subway and you want to go in. The experience of you going through the crowd into the bus or into the train would be equal or would be the same thing as the experience of people from the train going out through you. That's the reason. That's the explanation. All right? Now, we discussed earlier that this diffusivity has unit of meter square per second. Don't be confused. This is not acceleration. Acceleration is supposed to be meter per second square. This is meter square per second. And we have seen variable or parameters with this unit before 2 times. Oh, by the way, diffusivity depends on many variables. Let's say DAB, diffusivity. If your fluid is gas, then when temperature is increased, diffusivity increases. Okay? In order to understand this, just imagine you're in the room, and you are in the bus, let's say in the bus. And the bus, air conditioning in the bus is broken, all right? If one guy in the back remove the foot, remove the shoe, then you are sitting in the front would always smell something, right? The higher the temperature, the faster you smell something. That is this one. If you want to use pleasant example, just change the smell into, let's say, perfume. On the other hand, if pressure is increased, diffusivity would decrease. Why? Because for gas, the higher the pressure, molecules of gas squeeze together. So in order for one molecule to squeeze through it, it would be more difficult, right? So more difficult means diffusivity will get lower. For liquid, it would be the same thing. When you increase temperature, normally diffusivity would increase. Okay? This behavior is generic behavior. It's not, when you go toward special circumstance, for instance, if you want to consider gas at near critical point, that will be totally different. This is description in the generic term. Now, DAB sometimes is called mass diffusivity. It has unit of meter square per second. We have seen another 2 variable with the same unit, alpha, which is K over rho Cp. This is called thermal diffusivity. And then from the momentum section, nu equal to mu over rho. This is called kinematic viscosity, or sometimes can be also called momentum diffusivity. All right, all of them has the same unit. So therefore, we can play around with this pair, with this group. If I start with nu divided by alpha, we discussed this already in the energy session. Whenever we have momentum transport together with energy transport, in other words, whenever we have convective energy transport, remember when we have convective transport, it requires the flow. The ratio, this ratio would appear. This ratio is called Prandtl number. We discussed this already. What about another ratio? If I take nu over mass diffusivity, DAB, this is called Schmidt number. Okay? So whenever we have flow of fluid, and we also have diffusion of mass inside that flow, of course, it would be called convective transport of mass. We will always get this dimensionless Schmidt number. And then lastly, if I take alpha divided by DAB, so that means whenever we have energy transport together with mass transport, then this ratio is called Lewis number. All right, these are three dimensionless variables that should always appear when you have combination of transport phenomena. All right, so far we have discussed about molecular transport of mass transfer, just molecular part. But we realize that there are two parts, molecular transport and convective transport. What about convective transport of mass? By the way, these contents are in chapter 17 of the textbook, Bird Stuart Lightfoot textbook. Okay, it's in chapter 17. So let us look at the system. This is Y, X, Z, as we previously done for mass, for energy and momentum. If we have velocity, let's say velocity in any direction, V, going into the cube, if this area is called ds. Okay? So for convective transport, you have to imagine mass being carried by the flow. But that mass should not have ability to move by itself. How can you imagine that? So just imagine you have flow of liquid and mass of your interest, let's say you have flow in this direction. Mass of interest, let us consider a small bead. Let's say this is plastic bead. This bead, if you have to imagine this bead have the same exact density as the water around it, so it does not sink, it does not float, okay? It does not go up or down. It goes along with the flow. So the faster the flow rate here, the faster of this bead would travel. This bead cannot travel by itself. It does not have its own power. It can only go along with the flow. All right? So from now on, we just consider our molecules like this. So if this flow carry a bead into the box, and if you imagine you have more than one bead, you have a group of beads in the flow or in the stream of water. If you calculate or determine mass flow rate of my species A, which is my bead, okay? Let us focus in x direction first. And this is mass flow rate carried by the flow. So you have to understand, because my bead here has no power, so its velocity would be exactly the same as the velocity of the flow. Okay? So if I expand this velocity component to Vx, that means my bead traveling and entering this box should have x component velocity to be Vx as well. So the mass flow rate in x direction is basically linear velocity, Vx, times the area perpendicular to that velocity component. So that turns to be the volumetric flow rate. Okay, this is meters per second, this is meter square. You end up with meter cubed per second. If you multiply by density, or not density, by mass concentration, rho A. This is kilogram of A per cubic meter, and this is cubic meter per second. You end up with kilogram of A per second. That is mass flow rate. And remember, by itself, it has no power. It follows the velocity of the flow. So if I take this ds to the left-hand side, I have mass flow rate per unit area. That would be mass flux. And it is done by the flow. So this is convective mass flux. That would equal to rho A times Vx. Okay? So in similar manner, if you imagine a box here, rho A is a kilogram of A within that box. And the unit would be kilogram of A per cubic meter. And you multiply by Vx, which is meter per second. This meter would be in x direction. So if you take meter or distance in x direction to cancel one of this, dimension in x direction will be gone. You end up with this area, this highlight area. So this is the traveling in x direction per unit area perpendicular to it. So that's why it's called mass flux. Okay? So if you repeat the process for x, y, z direction, you will end up with combined convective mass transfer flux to be rho A times V. This is vector. Now flux will become vector. Okay? Now, once we got molecular transport or diffusion flux, we got convective transport of A, flux as well. When you add them up, it is called combined flux, and we use N to represent combined flux. So this is combined flux of A. One thing that you have to realize, this convective transport flux, rho AV, we explain this one with respect to this axis. So the box is fixed. So if the box is fixed, that means this velocity component is considered with respect to stationary point. Unlike this molecular flux, which is considered with relative to the flow of the whole population, this one is stationary. This one is considered with respect to the stationary point. Okay? Now, if I expand this JA to be rho A, VA subtracted by V, even though earlier we said VAY subtracted by VY, but now we combine all directions together, so you get generic VA vector and generic V vector. So this is velocity of the mixture, or velocity of the solution. And you have to realize now this V will be velocity of the solution as well. So Now, when you add them up, I change from these plastic beads to actual molecules that can move. So part of the molecules being carried would be this part. And part of the molecule that can move by itself would be this part. Okay? So if you add them up, this is rho AV. So you see that this part and that part would cancel out. Eventually, you end up with rho AVA. Okay? So don't be confused. You have rho AVA as a combined flux. But when you consider convective flux, it's only rho AV. These two are very similar but totally different in the physical meaning. Now, this part, I have to go slowly. Now, if I have species B moving slowly, species A moving quickly, of course, average velocity is supposed to be in between. All right? Now, if I want to find actual mass flow of B, actual mass flow of B is basically a result from combination of convective flux and molecular or diffusion flux. So actual mass flow of B is related to NB. So this would be NB. If I consider in y direction, that would be NBY. Right? So that would equal to, just like species A over there, that would be rho B V B Y. Okay? So that means I'm bringing mass concentration and multiply to this vector. However, if I use mass flow calculated from bulk flow, so in this case, if I consider bulk flow, that means if I assume that B itself does not move, okay, just like plastic bead. B is carried by this flow. Then the flow or the flux would be rho B V Y. This Vy is the mixture velocity. So this is the whole mixture carrying B. All right? And if you compare these two terms, you see that VBY is shorter than Vy. So that means this term is too fast. This term cannot represent the actual velocity of B. It's too fast. So calculating based on the flow of the solution, the whole solution only, is too fast. So you need to compensate with something. That something is molecular transport. Okay? So you need to get correction with diffusion transport or diffusion. And diffusion of B, on average, fluid is moving to the right. But relative to the flow of the fluid, B is much slower. So if you move your camera or move your drone around with this velocity, you will see B going backward. That means, according to the definition of diffusion flux, you take VB, subtracted by V average, you end up with this flux, JBY. And according to this picture, JBY is going backward. This number would be used for compensation. So this flux for the whole solution is moving too fast. It cannot be used to represent actual velocity of B. You need to add with this so that you get the correct value. Okay? So basically you get NBY by using the flow of the whole system corrected by the movement of each molecule. Okay? That's according to this equation. Now, if my system, I have A, B, C, so I'm going to have flux NA, flux NB, flux NC, and so on. This is basically summation of all fluxes, all species. According to this left-hand side board, NA would be rho A VA, NB would be rho B VB, and so on. Okay? Now, rho A is basically omega A times rho. Rho B would be omega B times rho as well. So if I take rho out, inside I get omega A VA plus omega B VB plus omega C VC and so on. This, once again, is the weighting average of individual velocity, weighting by mass fraction. So this is average solution velocity or mixture velocity. So at the end, you get rho V. Now we have seen this combination 3 times. First is rho A VA. Then we have rho A V. And lastly, we have rho V. They are different, and you have to make sure you can distinguish them. Rho A VA, the property of A, that's the combined flux of A. That's NA. Rho AV, this is mixture velocity carrying A. So this is convective transport or convective flux of A. Okay? Rho V, this is total of the whole fluid. So this is summation of Ni. Don't be confused about these 3. Okay? We will use them all the time. All right, so let's go back to this definition of combined flux. And also summation of Ni equal to rho V. In other words, V would equal to summation of Ni divided by rho. Okay? If I take this here, I will get JA plus rho A divided by rho times summation of Ni. This would be omega A. All right? So for binary system, I'm going to get Na equal to Ja plus omega A summation of system, and we have 2 species in the system, so that would be Na plus Nb. Furthermore, if I consider binary system, this diffusion flux can be represented by Fick's law. That would be rho dAB del omega A plus omega A NA plus NB. This will be used repeatedly in shell balance. Okay? But you see right away in this is combined flux, and this flux will be put in shell balance just like what we did in momentum and in energy, right? We set up shell and we put the flux, combined flux in and out, put into balance. But this would give you two problems. First, combined flux that we want to use now appears on both sides of the equation. That's one problem. Secondly, we have combined flux of another species appear in the equation for species of our interest. So we have to deal with these two problems. And I'm going to show you how to do that using examples. All right? Lastly, we set up everything using mass concentration. The unit here would always be mass. Okay? We determine, we start with rho A, which is mass concentration. The unit would be kilogram of A per cubic meter of the solution. I can change mass basis into molar basis. Molar basis would have unit of mole of A per cubic meter, or this is molar, just like in chemistry. Conversion can be done by using mass concentration divided by molecular weight of your species of interest. Okay? So therefore, from this side, if I divide the whole board into half, total concentration can be calculated by summation of mass concentration of each species. In the same manner, if you take summation of molar concentration of all species, you get total molar concentration. If you take rho A divided by rho, you get mass fraction. In the same manner, if you take Ca divided by C, this is mole fraction. Let me write it, this part. Okay? Mass fraction, mole fraction. So in the sense, if we take, let's say, omega A times VA plus omega B times VB plus whatever we have left, how many species we have, this is mass average velocity. So this is fluid velocity or mixture velocity averaged by mass. And I said from the very beginning, this is one way to do it. Another way to do it is to use molar fraction or mole fraction times VA XBVB plus everything. This one will be average velocity as well. The problem is, you know that mass fraction and mole fraction are not the same. This VA and that VA are the same, but when you weigh them differently, the results are not the same. So this, we put star over here just to say that this star means the average was done on molar basis. Okay? We have diffusion flux, JA, equal to rho A, VA subtracted by V. If we repeat the same thing, taking molar concentration times VA subtracted by V star. Now it is also diffusion flux, but in terms of molar basis, we call this one capital JA star. Okay? For the flux, capital means molar basis, star means width relative to average velocity calculated based on molar average. If you use Fick's law, that can be written like this. I can apply Fick's law in molar basis as well in similar manner. Ca, dAb, del XA. Okay? Please note that diffusivity here and there are exactly the same. So for convective transport, convective flux, it is rho AV. For molar basis, convective flux would equal to CAV star. Okay? And then we have combined flux equal to rho AVA. Combined flux in molar basis would be capital NA equal to CA VA as well, vector. Okay? If you sum it up, summation of NI, that's equal to rho V. If you sum on this side, summation of molar flux would equal to C V star. All right? Now, for this equation, for binary system, then combined flux A would be consisted of diffusion flux and convective flux, which is XA NA plus NB. Exactly the same form. And you can use Fick's law. This would be dCAB, CDAB, del XA plus XA NA plus NB. Exactly the same form, just change from mass basis to molar basis. And depending on the situation, we can use either one. Mass normally would be used because equation of motion that we derive in momentum part has density in it. So density is related to mass basis. So we are going to use mass basis normally when we apply it to the equation of motion. On the other hand, whenever you have reaction, chemical reaction is represented by stoichiometry ratio, which is in molar basis. So this equation will be more convenient if you have reaction in your system. All right? So that's everything in chapter 17. Next time, we are going to put them into the shell balance, moving out to chapter 18, and give you examples how to deal with each situation. All right? See you next time.